All right, welcome back. Okay, so in our previous lecture, we have finished the part for backpropagation algorithm, which is an algorithm for computing the gradients for a shallow neural network. And that idea of backprop the gradients from the future layers to the previous layers actually is a universal algorithm that can be used to train very large networks like the deep neural network that we are going to talk about today. Okay, so so far so good. The backprop seems a very promising method. That's because it clearly defines how the gradients propagates from later layers, like given the disease we know, and then we're able to compute basically everything, the gradients of everything before that layer, before the current layer. So technically we can know the gradients precisely, and then we can use the gradients to update the parameters using gradient descent algorithms. Okay, and the fact is that to apply such an algorithm like backprop to train a very deep neural network is actually still a very challenging task. Okay, because when the network is pretty deep, then it'll be problematic if we do not do anything to make sure that the gradients will successfully pass from the later layers to the previous layers. And this is just one of the issues that we're going to deal with in a deep network. There are tons of details that help us to better train a network, to train it with more, first of all, more quickly. Like we want to train a network efficiently without spending too much time waiting for the updates of the parameters. And also we want to make sure the resulting model is effective in making predictions, is useful to the testing data set, so that we still need to consider issues like overfitting, like we want the model to generalize well. Okay, so this is particularly an issue because the model that we are training now is a very deep model, which means there's a lot of parameters. And that many parameters means it's very likely to overfit with data if we don't take any steps to regularize the model. All right, anyway, on this slide, it basically summarizes the contents that we're gonna talk about in this chapter. So as you will see, I basically summarize them into several sections. And first, we're gonna go through the basics of the concept of building deep networks. So it's basically an extension of the shallow network, but we're gonna see some interesting technical details, okay? And also, we'll focus on several parts. The first part is how to make the training faster, okay? And we will talk about how we prepare the mini batch for gradient descent. And for the second bullet here is a bunch of methods that are related to the optimization algorithm. So we'll introduce momentum RMSProp and add-on optimizer, and together with the learning rate decay. Okay, and actually the batch normalization and batch norm is something that we're going to introduce at the end of the class. Okay, although it belongs to the category that with batch norm we want to make the model training faster. Okay, and the second category is about the overfitting issue. Okay, we have so far covered this issue several times. When we talk about logistic regression, we use L2 regularization, right? And this L2 regularization basically applies to any kinds of models. And in neural network particularly, we will introduce this special type of technique called dropouts, which I also mentioned in the previous lecture, right? I received some questions. So these dropouts is way to basically solve the overfitting issue, to, well, not totally solve the issue, but to make the model generalize better to testing data sets. Okay, we'll also mention a little bit data augmentation, because this is also a way to deal with overfitting. And lastly, we're gonna talk about the vanishing and exploding gradients issue. Okay, because it's when the model is deep, this issue is very oftenly observed if we don't take any prevention steps. So we'll talk about how we initialize the weights properly and how those better initialization will help eliminate those, help prevent the vanishing and exploding issue. And also clipping gradients is another common practice. Yeah, so that's a lot of contents, and hopefully we can cover this in 2 lectures. And of course, in these slides, I will go through some of the details. And fortunately, our current technique advance makes sure that we don't basically need to implement those techniques from scratch. But I think it's still necessary to know about how exactly these techniques are doing and what the underlying mechanism is. If we don't know how the underlying works is going, how the details is, then it's basically just terms. Yeah, we just can call this. We can just implement this in PyTorch by calling the correct arguments. Okay. All right. That's pretty much for the introduction, and let's get into the basics first. So far, the examples we have shown here is from the previous lecture. It's a 2-layer neural network, right? So if we extend it to like multiple layers, even more layers, then this will be the so-called deep neural network that we're gonna focus on today. Okay, so let's go through the notations again as a simple review, as a brief review. Okay, so the capital L is the total number of layers. So we're not considering the input as a layer, right? We're just counting from the first hidden layer. That's 1, 2, 3, 4, 5, right? And the hidden layer, if we want to indicate it as a layer, then we probably can use 0. It's about layer, and the N with superscripts and the L in square brackets is used to indicate the number of units in that particular layer. All right. So the first layer has 4, second layer has 4, and so on. 4 units. AL is the activation for that layer. All right. That's lowercase a. And W and B are the parameters associated with each layer. Okay. All right, and then let's review the forward propagation or forward pass, which is basically more or less the same as the shallow neural network. If we use a single data example in lowercase x, okay, as the inputs, so everything about the z and a's are all in lowercase because it's just one data instance. So the forward pass will be like Z1 will be computed first, and Z will be fed into some activation, and we got activation. The activation at the previous layer will be fed into the next layer, and so on, right? So if we vectorize over M examples, it's by stacking all the data points into column vectors. So now we have capital X, capital Z, capital A. Everything, each column in that capital Z and A will be a column vector. Okay. And then in the backward propagation or the backward pass, we will start from the output layer. In the output layer, it's determined by how we want to compute the loss or the cost function. in a binary classification case, the loss function is the one that we use for logistic regression. And from that loss, we can compute the gradients of the last activation, which is DA5. Okay, from DA5, we can compute DZ5. All right, from these layers, we go backward. And of course, the parameters for DW5 and DB5 will also be computed. Okay, so here in the computation of DW, the activation from the previous layer is already used. Okay, and then from this layer on, we go backward. You can compute DA4, DZ4, DW4, DB4, and so on. Okay, so the simple example, simple data example, and the vectorized example, they are also correlated, like in a similar way to the forward pass. We just need to like replace the lowercase letters with the uppercase, or with the uppercase letters. Okay, a little bit different is that the how we compute dB is that we will compute the per level per row summation, the row summation. So if it's in numpy, so it'll be something like indicates the axis to be 1. Okay. All right, that's the backprop for the deep network. Okay, one thing that we noticed is that in the computation of DZ and DW, we not just use the gradients from the later layer, but we also reuse the values computed in the forward pass, because the Z's is computed in the previous slide when we do the forward pass, and the AL-1 is also the activation that is computed during the forward pass. Okay, so when we actually implement the network, we need to reuse those values. Okay, we need to after the forward pass, we need to store these values into some cached memory, because they will be used in the later backward propagation step. All right. So let's zoom into each level, each layer, just focusing one layer, and we use the green color to indicate the forward pass. Then for this particular layer, L, the input would be AL-1, and output will be AL. So after this forward pass, as we said, we want to cache the ZL. The ZL, which is WL times AL-1 plus BL. And also we want to cache AL-1, because these two will be used for in the later back propagation step, right? In the later back propagation step, when we want to compute DAL and when we want to compute DAL-1 using DAL, we need to use the ZL. Okay. All right, and for the computation of WL, DW, and DBL, we also need those cached values. All right. Okay, so if we modularize this a bit, we don't want to like draw all those circles, all those connections, and we simply use some more like compact view of this layer per layer of the neural network. We can simply use a box. Okay, use a node to indicate one layer of neural network. So it's just a summarization from the previous slide. From AL from AL-1 to AL, it's the forward pass, right? And after forward pass is done, we're gonna cache the AL-1 and ZL, because they will be used in the future computation of in the backward step. Okay, that's one layer. This is a very compact view of the network. Okay, and to showcase how a deep network works, we just stack all these layers, all these building blocks, right? This is the forward pass for layer 1. From layer 1, we go to layer 2, right? Same, the similar cache will be, the cache step will be executed, okay? And next, layer 3, oops, right? And until we hit layer L, which is our final layer. And the final layer will output, use the activation as the y-hats. It will be used to compute some gradients. Those dA will be backprop, will be the first step of the backprop, which will be propagated backwards to the next layer, right? And to the first layer, right? So all the dBs and dWs, those are the gradients. Okay, so these are the most useful piece of information because we want to use those gradients to update the value, update the parameters, right? We collect all these dWs together, and then we use the formula of gradient descents, right? Remember, this is the formula for gradient descents. And the alpha here is the learning rates that we control how much a step we want to make in each iteration. Okay, so using these gradient descents, we can update the parameters W and B accordingly in the hope that we reached some minima points, global minima points. So that'll be the result. That'll be the where we end when we train the model. All right, that's a complete workflow using the concept of computation graphs. All right, so let's give me a second. I need to open the door. Okay, so next we're gonna look at the actual code in Python if we want to implement such a network using NumPy, right? So this will be the code that you will read in the homework for deep neural network. I think you already saw this in shallow neural network, which is basically the similar syntax, similar formats. We will need to define the forward function for the linear layer, right? It will be the z that will be returned. And here, other than z, we also have the cache, okay? The cache will be the activations stored, okay? And the values for b and w, w and b. Okay? Then in the forward function, there will be two steps of the forward function because there's a linear forward function followed by the activation function in which we use ReLU. Okay, of course it can be other functions. Okay, and the forward function also returns some cache, which is a linear cache and the activation cache. So these are the details. It's not necessarily like this if you implement it in a different way. It's just for your convenience because in the homework we're gonna have several steps in implementing a deep network. Okay, and the next is the backward. So the backwards, because we in the previous forward we define the cache. In the backward step, we will take into the cache as the inputs, and we need to like depackage the cache, right? Like take all the variables out of the cache, and those variables, the previous activation, the W and B will be used in computing the gradients for W, B, and the previous and the activation of the previous layer. Okay, and similarly in the backward step, we need to use those cache properly. Okay. So the ReLU activations backward step actually is something that you will not need to define yourself. In the homework, I will provide it as a predefined function. Okay. All right, that's a little bit knowledge of using Python, and actually, in the next few slides, I will show the result of the code for using PyTorch, which is much more powerful tool than just using NumPy. Okay, in PyTorch, you don't need to care about the details of how the backward step is actually conducted, but technically there should be always some cache stored from the which are the results from the forward pass. All right, so a little bit knowledge about why we use deep network. Okay, so far in our example, in our assignment example, the shallow network and the logistic regression actually works pretty well, because the accuracy is pretty satisfactory in the image classification task, right? But for more advanced tasks, the deep neural network will show its advantage. Okay, and the basic principle of why deep network works is that it's about the resulting encodings of from the layers at different position, from the units at different layers. Those earlier layers that are closer to the raw data, they represents the encodings from those layers represents lower level features, such as the edges in the raw image, or like different parts in the image. And then as we go from the bottom layers to the higher layers, the higher level layers, they represent larger, they represent more abstract or higher level features, like different regions on the face, different types of the face, different types of higher level features. So that is basically why deep network works, because we are not just using the lower features, but also use some of the combinations of the lower level features as some higher level, more abstract representation of the images. Okay. All right. Next, let's look at an example of PyTorch. So, in the previous two lectures, we have gone through the PyTorch example for the back propagation stuff, right? So now, because it's so-called deep network, and in PyTorch, we can basically use the NN dot sequential. So use this module to like wrap up everything we have defined for each layer. So in this sequential module, it takes the inputs, right? It takes input a linear layer, a ReLU activation, another linear layer, right? So although this is a very shallow, it's just 2 layers, and the second layer even doesn't have an activation. So it's just in showcase an example, but technically, theoretically, you can add more layers. It can add as many layers as you want. Okay, and it's a rather very convenient way to define models. Oops. And another way, so this method, rather than using the NN sequential, it actually it's a more flexible way to recommend, and it's also recommended. And like we define a module, I think I have talked about this in the previous lecture, right? We define the module as a subclass of the NN module, and we in the constructor initialize function here, we define all the parameters, all the layers, right? In the forward pass, we take in the forward function, we takes the input as an argument and then define how we want the forward pass to compute. Okay, it's a lot of flexibility here. We can do whatever transformation, whatever computation we want to do here. And one more thing is that the previous step, the previous method, style 1, here we use sequential, right? And we can actually apply the sequential within this initial line. We can define a sequential here, define a model using a sequential within the body of the initialize, and we call this sequential module within the forward, which is totally acceptable. Okay, so that's why I said this style of defining model is much more recommended. Okay, all right, that's the basics of deep network, how deep neural network works in computation graph in theory, and also in Python, in NumPy and PyTorch practices. All right, so now we gonna step into the realm of actually training a network effectively. Okay, because this is not a very easy task. There's a lot of places we need to pay attention to. So first of all, we'll introduce the two terms a little bit: parameters versus hyperparameters. The parameter is a term that we used a lot, right, very often in this class. So it basically refers to the variables that comprises the model. Okay, the model consists of a bunch of parameters. Those parameters are tunable. We can change it, right? We can update them dynamically during the training, and though they actually represent the model. Okay, those models are so-called trainable variables. Okay, but also other than parameters, we will have other variables called hyperparameters. Okay, those hyperparameters, the biggest difference is that they are not they don't receive gradients in the model during training. They are not part of the model. Okay, they don't contribute to the model. They are just the configurations that we set up before the training stage starts. Okay, like the learning rates, right? Of course, learning rates can be adjusted during the training, but it's not determined by the gradient descent algorithm. Okay, it's not like we receive some gradients for the learning rates. It's not like that. It's just by manually changes according to our experience, according to our empirical results. And other than learning rates, we have a ton of others, like a mini batch size, number of layers, what kind of activations, right? So these hyperparameters, we're basically gonna cover some of them, because when we talk about the techniques of how to train a model efficiently and effectively, we're gonna deal with some of those hyperparameters in those slides. Okay. So we need to, given these parameters and hyperparameters, we need to choose the proper optimization techniques, okay, and the proper methods to tune those hyperparameters in order to improve the performance of the deep neural network being trained. All right, so the hyperparameters that we will first talk about is not learning rates or number of hidden units, number of layers, but we're gonna talk about several special types of hyperparameters. The first beta is the beta for momentum. Okay, we don't know what momentum is, but it is a hyperparameter here. And also the beta 1, beta 2, and epsilon for the atom optimization algorithm. Okay, and we'll talk about the learning rate decay and the batch mini size. Okay, so we'll just first mark those terms here, momentum, atom. Okay, we're gonna cover them later. Okay, and all we need to know is that those methods comes with some additional hyperparameters to be tuned. Okay, the first one we're gonna talk about is the mini batch gradient descent. Okay. Okay, so a little bit brief review of the previous contents. When we introduce gradient descents, we talk about batch gradient descents, which utilizes all the data sets, all the data points in your data sets, and the mini batch gradient descent, right? Mini batch is somewhere between, it uses part of the data, okay? And the purely stochastic gradient descent is something that people rarely use actually nowadays, okay? So batch gradient descent will be problematic if we have a very large data sets, because we don't want to put 2 million data points into the memory, right, into our computer memory, right? So we will split a reasonable strategy is to split the training set into mini batches, and each has size like it's just an imaginary number. It can be a random number, right? We can, for example, set the size for each mini batch to be 1,000. Okay, like this. So we can basically partition the whole training sets into that many folds, and each fold contains 1,000 data points. Okay, we place those boundaries in there, and we can call the first part of the data set to be x1, which is in the curly brackets. Okay, that indicates the first mini batch and the last mini batch. Okay, and accordingly, we need to do the same thing to the y's, because the x and y, they are in a 1-to-1 mapping relationship, right? We need to remember which x corresponds to which y. We should always keep the mapping relationship. So we also have y in the first mini batch, second, and the 2,000 mini batches. All right. So in this particular example, we have 2,000 mini batches. Okay.
On that slide, on the previous one, I think there's a minor typo that you might want to address. In the y of 2 section, it says x to 2,000.
Oh,
and that should probably be a y.
Yeah, all the remaining parts. Yeah, good catch. Yes, these should be y. Thank you. Okay. Now let's look at how the mini batch gradient descent works. Okay, we actually have, I think we have talked about this. It's quite similar to the gradient descent method, but this time we just explicitly define the number of mini batches and the size for each mini batch. So because we have 2,000 mini batches, so if we want to go through all of them, we need to use a for loop, right, to go through each one of them. And in the forward propagation step, we will use that one mini batch, okay, x of t. Okay, the t indicates that is the t's mini batch. Okay, in that mini batch, in that forward pass, we compute the z's, a's, and then to the last layer. Okay, and these are optimized, are vectorized over 1,000 examples, because there's 1,000 data points in the current mini batch. And the cost, the final cost function, the cost value, will also be computed upon these 1,000 examples. Okay, and the gradient descents will be based upon using the yt as the ground truth, and the loss will be the gradients will be computed, and the gradients will be back propagated and used to update the parameters. Okay, so if we have gone through all mini batches in the data for once, then that's said one pass over the entire data set, and that's what we call one epoch. Okay, so one epoch is a one complete pass of the total data sets. Okay, and the number of epochs is something that we we will like experiment on. Like we don't know how many epochs is the best option, but usually we given a data set, we will at least go through all the data points for once, if the data set is not ridiculously large. Okay, and as we know, for large data sets, mini-batch gradient descents will run much faster than a batch gradient descents. Okay, so let me just show these plots again, which shows the difference. So the number of epochs, I think it's more just intuitive. If your data set is small, then it makes sense you go through, you set higher epoch numbers. Yeah, if the data set is very big, then it depends. Depends on what your task is. Yeah, so these three graphs are something we have already shown before. It shows how the cost will decrease in different types in gradient descent versus mini batch gradient descents. In batch gradient descent versus mini batch gradient descent. So the mini batch gradient descent, the cost will fluctuate, but it has a trend to go down. Okay, and these cost plots is something you will need to observe to determine when you want to stop the training, when you want to conclude that okay, it's a model, it's almost done. Okay. And these contour plots is like how different methods will approach the theoretical minimum points. Okay, so the batch gradient descent is like a straight line from the starting point to the theoretical minimum point. But the mini batch will take some alternative directions. So it will take more steps, but because each step is much faster than the batch gradient descent, so the mini batch is in this case is a better option than the mini than the batch gradient descent. All right. Another question arises with mini batch gradient descents is how big we want to each mini batch to be. Okay, this is a very intuitive or empirical question. Typically, people would choose numbers like 64, 128, something, because people believe that it'll be faster. Theoretically, it'll be faster to be accessed for CPU and GPU because those numbers are 2 to the power something. But it's not a super strict requirements. I also saw something like mini batch equals 100 or so. Yeah, that's not that strict requirements. One principle is that if each data point is very big and your model is very big, you have a lot of parameters, then you will need to be careful about using a mini batch size that is too big. Okay, because it will probably not have a CPU or GPU memory that is big enough for taking all the data as inputs. Okay, so that is the principle for mini batch, for choosing a proper mini batch size. Okay, we have reviewed the mini batch, the gradient descent. Okay, so it is now time to talk about the momentum that we first marked down in several slides ago. Okay, all right. So in a short sentence, momentum is an algorithm to make your optimization algorithm run faster. Okay, if it's a pure gradient descent and we don't do anything else, sometimes it would be take very long time to converge to find the theoretical minimum points. Yeah, so the momentum algorithm or the momentum method is a way to solve to improve the issue with gradient descent. Okay, and we know gradient descent uses the gradients to update the parameters. Okay, momentum's idea is that we don't use the gradient directly. Okay, but we need to use gradients. But we first compute the exponentially weighted average of those gradients, right? Then we use these average gradients to update the parameters. Okay, we don't directly use it, but we use an averaged gradients. Okay, I think the idea is very simple. Okay, and the intuition behind is also quite straightforward. So for example, this very long ellipse shows the contours of some cost function. Okay, we start from somewhere and we want to reach the red dots in the middle. Okay, that is the theoretical minimum point. And usually, so if we don't use anything with momentum, if we just use raw gradient descent, then because the contour is very flat and the direction of a gradient is always perpendicular to the contours. Okay, so because now the contour is in a not very regular shape. Okay, so for example, if we start from this point, and since the gradient's direction point is perpendicular to the contour, yeah, so the gradients, each step of gradient descent will probably let us go upward, right? It's a direction that is not pointing towards the minimum points, right? It's pointing upwards, although it's still closer to the minimum point, but it's not a very efficient step. So if you go from that, take the first step like this, and then we take the next step. So you see, it is true that we are indeed approaching the minimum points, but we are like not very efficient. We are taking extra steps to explore the upper space and the lower spaces, right? So these fluctuations, those jigsaws are just unnecessary, right? If we can make some adjustment towards where we go in each step to make it more oriented towards the minimum point more directly, then our problem will be solved more quickly, right? So how do we eliminate these oscillations? Like we don't want to go through directions that are far away from the minimum point. That's what momentum proposed to do. Okay, so basically in each iteration, we compute the gradients for W and B as we usually did, all right? But now we will compute something called a velocity. So this V is for velocity. We compute the velocity of the dW. Okay, dW is the gradients for W. So what is velocity? Velocity is beta times the previous value, the previous velocity, plus 1 minus beta times the new gradients. Okay, so velocity is the average between the average of itself and the new gradients, right? And similarly to same thing will be applied to the gradients of B. Okay, then in the update step, we don't use the gradients, but we use the velocity. Okay, in the update step, remember, previously we used dW, but now we use velocity. Okay, so a direct outcome of this is that since the velocity is the average results of velocity and the gradients, okay, it's much more smoother. Okay, these velocities are much more smoother. So if you, as I showcase in this example, if we smooth the gradients, then the opposite directions will eliminate each other, right? If we go up too much and down too much, then these two opposite directions, those opposite components will eliminate each other because they point to opposite directions. So the results of this smoothed velocity is that they will point towards the directions much more faster, right? So the horizontal oscillations are averaged out. So if you count the example here, it takes 1, 2, 3, 4, 5, 6, 7, 8 steps for the blue points to move towards the current position. And the yellow steps is only takes 4 steps, right? So basically an MA on the gradients. So by MA, you mean moving average? Yeah, okay, moving average. Yeah, it's kind of, it's like, I mean, by moving average, it's kind of suggesting that you have a sliding window, right? Along a time series. And in the case for momentum, it's actually taking all the historical information, like in the VD here, right? In the VD, the velocity of the previous step, right? It actually contains all the historical information. So technically, it's a sliding window that starts from the very beginning as the left end, and the right end is the current step. Yeah, I'm not sure if that's a way to define motion average, but it's kind of the idea. Yes. Okay. All right. So it's called exponential weighted average. Okay. So here in this slide, we did a little experiment. Like if we consider the velocity at the 100 steps, it is the average between the velocity of the 99 step plus the weighted gradients, right? Weighted gradients at 100 step. And for other steps, we have the same formula. We can like rewrite all the formulas. And if we can sum up all those equations, like we can have basically have like we substitute, right? If we substitute these seconds into this term here, right? We will have this extended equation. And if we do the substitution again and again, we will finally get something like the dW at the 100 step got a weight of 1 minus beta, and the gradients of the previous step get a smaller weight. 2 steps away, we got an even smaller weight, and this weight is basically decreased by the factor of beta, right? So it's kind of indicates the results is that the weights assigned to the nearer past is larger, okay, and the weight to the past gradients that are farther away are lower weighted, okay. So if we have some time series data like this, then the results of applying a exponential weighted average would result in some curves indicated by this blue curve. It's much more smooth, and the strength of this smoothing is controlled by the beta. Okay, so the beta actually indicates that how much we rely on the previous value or the current updates. Okay, so if beta is bigger, then the reliance on the previous velocity is larger, and the rho or the weights of the current gradients is lighter or less rho, or like less weighted. So there's a beta that can be tuned. Okay, it depends on how much we want to how aggressively we want to use the gradients, or how conservative we want to stick to the previous velocity. Okay. So basically, if we use larger beta, the smooth effect would be more salient. All right. All right, a little bit about the implementation. We need to first of all, initialize them to 0, right? So during the training, for example, we have that many number of iterations, and we compute dW and dB on the current mini batch, right? And then we compute the velocity, and then we update the W and B, and the common choice for beta is 0.9. I think it's the default values in most optimization packages, optimization modules. So it turns out that its momentum almost always works better than vanilla gradient descents. Okay, so it's almost a default choices nowadays. Okay. So that's momentum. And we'll look at the next type of optimization technique, which is called RMSProp. So it takes a similar idea, but it's utilizes a different way to do the smoothing, actually. So RMS is for root mean square, okay? But it's similar to momentum, but it uses a different mechanism. Right. So here's the result we want to achieve. Here's the effect. We want to smooth the gradients, right? So that the steps it takes becomes smaller, right? So the assumption. So if we look at the beta, the W and B, which are the two parameters. So the assumption is that there is relatively big oscillation along the direction of W. We'll assume that this is the case. So the solution is that we decrease the magnitudes of dW, right? That is a very straightforward assumption, right? Because we don't want to go that much unnecessary steps. So why not we just decrease the magnitude? Which is another way to put it. Another way, it is to be more conservative when we do the updates. We don't take that big step, because big step may be risky. It can lead to us to somewhere which is farther away from the minimum point. Okay, so that's for RMSProp. And the implementation of RMSProp also relies on some intermediate variable. So this time we call it S, okay? It's SdW and SdB, which are similar to the velocity, but they are computed in different ways, okay? So for the within each iteration, we computed the gradients first, right? And now this dW, SdW, is also the exponentially weighted average of SW and the roots and the square of the dW, which tells about the magnitudes of the gradients. Right, it's the exponential average between, or it's basically the average exponential average of the magnitudes of the gradients. Okay, so that's dW and dB. And when we update the parameters, we will use the normalized gradients. So it's dW, but normalized by the average magnitudes of dW, right? Because we average the values of dW square, and then we use the square root to make it a average the magnitudes of dW. And this plus epsilon is just for preventing the dividing by zero error. Okay, so for dB we use the square roots of the average dB square, actually. Yeah, so that is very, this method makes sense because we use the normalized version for gradients rather than the raw gradients. Okay, so and larger gradients means that larger SDW, and it will be used to normalize the DW. Okay, which means we have smaller oscillations. All right, so in order to distinguish from the momentum, we will use beta 2 actually, rather than beta, okay? So that's two betas now. We have beta for momentum and a beta for RMSProp, okay? All right, and then having these two methods, then it just makes sense. Why not we just put this together, right? We have two pretty fancy methods, and why not we put them together? So if that's, then we will have ADAM, which is short for adaptive momentum estimation. So ADAM is currently nowadays a default choice when we want to train basically whatever kind of neural network models, okay? Because it's a combination of both, we need to have velocity and these S defined. And in each iteration, we compute the velocity using the beta 1. Notice that we have two betas, so we will use beta 1, right, for the momentum, right? And for S, we use beta 2, okay? And then we will compute something called the velocity prime and the S prime. So these are the bias correction term in order to speed up early stage learning. Okay, so basically it's like when the t is very small, these like t is very small, these will be pretty large ones. So that's the training will be jump started. Okay, and the values that will be used to make the updates is based on these combination, these velocity and the normalizing term here, right? Okay, so it's the combination of both methods with momentum and RMSProp. Okay, all right. So in modern frameworks like PyTorch, if we take a look, we basically need to use this Optim package. So it's something that you can directly use in PyTorch. Okay, it's a very good, useful package that abstracts the idea of all the optimization algorithms. Okay, so you don't need to implement all the details. So, for example, the SGD, the raw stochastic, the raw gradient descent. So this SGD actually does not mean that we are just using one data instance. Okay, it's just a conventional, for conventional reason we use SGD here, but it doesn't require that you just use one instance. It can be mini batch gradient descent. Okay, so this package, you can define it by telling it which parameters you want to update. So we tell the SGD class that we want to optimize everything in the model, okay? And we tell that the initial learning rate is that value. So how we do that is to, in each iteration, we will first use it to put all gradients to 0, okay? And then we carry out the backward step. In the backward step, we'll recompute all the gradients, okay? And then we use the optimizer dot step. This will automatically update all the parameters contained in the model dot parameters here. So we don't need to do that manually, okay? That is very easy to use. And in PyTorch, actually it's very easy to indicate how many momentum you want to use, okay? And you don't actually, in most of the cases, we don't even need to change those default values, okay? Probably learning rate is something we can change, but the momentum is something that we don't oftenly change. Like we can define the momentum, we can indicate the momentum in SGD optimizer, and more oftenly, we will use ADAM directly, okay? But the default values is something that we don't often change a lot. Okay, so it's very easy to define and call an optimizer in PyTorch. All right, so I think we have time to cover the learning rate decay. Okay, so we have actually talked about this when the first time we introduced gradient descent, right? Because the mini batch gradient descent, in theory, it will never converge to the theoretical minimum points, because the cost of the cost function is defined on all data sets, but on all the data points. But within each iteration, we'll just use part of the data set to estimate the gradients. So that gradients is not an accurate, theoretically accurate estimation. So we will always eventually go very close to the minimum point, but we will zigzag around that area. So it's necessary that in the later stage of the training, we need to slowly reduce alpha. Okay. So, because in theory, it will always wandering around the minimum points, and we need to take smaller steps when we are getting closer to the minimum points, as indicated by this green curve. Okay. So actually, a lot of choices, like we let the learning rate decay with inverse proportional to proportionate to the epoch numbers, right? And we specify some decay rates, right? And we start from some initial alpha 0 initial learning rate, which is 0.05. Okay, and we can also use exponential decay, right? Or use these other different forms of decays, all kinds of decays. And in PyTorch, in practice, it's something called a learning rate scheduler. Okay, so this learning rate scheduler, if we call the step learning rates, this is a way to decay the learning rates when you have a lot of epochs. Okay, for example, if the epochs is is less than 30, then we'll use a larger learning rates. If it's between 30 or 60, we'll use a smaller learning rates and even smaller learning rates. Okay, so this step size is something you can define yourself. Okay, and this gamma will control how big the factor of decrease of the learning rates. All right. We still have some time, so why not we just finish the L2 regularization, which I think is pretty briefly gone through and going through. So for the dropouts, I think I will leave it to the next week. Okay. So again, talking about regularization, the purpose of it is to prevent overfitting issue. This is particularly important for deep learning, for deep neural network models, because we have so many parameters. Okay, each layer is a W and a B, right? And W can be very big because it's a matrix. If you have 50 in the input layer and 20 in the output layer, then you have 50 times 20, which is 1,000 parameters. That is a lot of parameters. So having those that many parameters, it's very easy to lead to the overfitting issue. So I'm not going to, so I quickly go through this overfitting issue here. So what we're gonna do is to, we already defined the L2 regularization for logistic regression, right? So what about we do the same thing for a neural network, right? That is also doable, okay? We just define the, modify the cost function by adding this regularization term, which is the inner product or dot product of the parameters with itself, okay, controlled by this lambda, okay. So this will change the way we compute the gradients for W, okay. So the gradients would be smaller if the lambda is if the lambda is properly chose, then the learned parameter w's will be having a smaller magnitude, right? So it's like a minimize the cost plus the complexity. So this is something from the logistic regression, right? So in L2 for the neural network, it's actually the similar thing, but now because we have multiple layers, it's basically the summation of all layers, okay? And the WL is for each layer. And this norm is basically in mathematics it's called a Frobenius norm, but in nature it's just the summation of all elements, right? Given a NL by NL minus 1 matrix, we just sum up the square of all elements in that matrix. Okay, this is just a fancy name for this similar technique. Okay. All right, and we can compute the gradients given the L2 norm, given the L2 norm included, and the results W would also be the similar form. Okay, so it's also called a weight decay. Okay, so in PyTorch, actually we can we don't need to manually compose this modify the loss function. Okay, we can just let the weight decay arguments to be true, or we can let it set up a parameter that control the strength of weight decay when we initialize the optimizer. For example, if we don't want to use the L2 regularization at all, then we can use the 0. Okay, to tell that don't carry out any weight decay. Okay, so this weight decay is something that we can try if we find that the model doesn't generalize very well. Okay, and it depends on situations. Sometimes people don't use that, but sometimes it's a little bit useful when the overfitting issue, or when overfitting is an issue. All right, that's so much for today. I think we will talk about dropout for the next time, for next Tuesday, and then that's pretty dense content today. And but these are all very common and useful practices in training deep neural networks, not just for deep regular neural networks, but they also apply to the convolutional neural network and the recurrent neural networks that we will introduce in the future. All right, are there any questions? Okay, no question.
Is there a quiz today, or?
Quiz today. Let me see. There's a quiz. Yeah.
Okay.
Let me check the questions to see. I don't think we apply Adam for linear regression. I didn't hear of people doing that. Yeah. Adam is usually used when the cost function is a very complex one. But for linear regression, we have very simple cost function defined, which we can get a analytical solution. So I don't think Adam is necessary for linear regression. So let me look at some questions for deep neural network. Yeah, I can. Yeah, I will. There's a quiz question today. Okay. All right. So I'm gonna stop recording now.